Like most big cities of the world, London has a problem. A traffic problem. Thousands of cars, buses, vans and lorries enter and leave every hour of the working day. Traffic jams and long delays are a normal part of metropolitan life. With an anticipated increase in traffic every year, many road improvement schemes have been put in hand. And where busy main roads intersect, flyovers have been built. In the centre of London, where space is at a premium, other methods have been adopted, and underpasses are playing their part in helping to keep traffic on the move. But in winter, flyovers and underpasses with their inclined approaches can be hazardous to traffic, unless steps are taken to prevent the formation of ice on the road surface. This flyover in the west of London has been installed with road heating electric cables, and their efficiency can clearly be seen in the sharp division between the heated flyover and the snow-covered, unheated approach road. At all times, this important link in the main road to the west of England is open to traffic. For years, a notorious bottleneck was Blackfriars, where traffic flowing north and south across the bridge intersected with traffic flowing east and west along the embankment. Here, the City of London Corporation put in hand a far-sighted road improvement scheme. Partly a flyover, but mainly an underpass, width has been added to the roadway by taking part of the river, so providing an additional carriageway for the east-west traffic and a slip road for the northbound traffic, leading onto the Victorian embankment. The authorities decided that here too a system of road heating should be incorporated. There are a number of different ways in which road heating can be carried out, but all based on one thing: a source of heat installed in the roadway just below the wearing carpet, with a heating potential sufficient to keep the road surface clear of snow and ice in all normal winter weather conditions. One system makes use of steam or hot water carried through pipes. But this means that steam raising plant must be installed nearby, and there can be serious delays in getting the required temperature should the weather turn unexpectedly cold. Another method uses mats of steel mesh supplied at low voltage and at a high current density. But this system requires large transformers and associated equipment, all of which adds to the overall cost. Experience has shown, however, that the best method is to use electric heating cables energized at the normal mains voltage, a system that is readily adaptable to a wide range of installation conditions. The road surface may be laid directly over the cables with a minimum of delay and without modification to materials or methods. For small or low-priced installations, the system can be operated manually or automatically by means of a simple air thermostat. For economy in operation, a moisture detector can be used in conjunction with the thermostat, so that heat is withheld until the temperature falls to near freezing. To this can be added a snow detector with a built-in heating element to melt the dry snow and so create the moisture conditions necessary for the operation of the control gear. For maximum economy, a time switch may be incorporated in the system to take advantage of the low-priced off-peak tariffs, and overriding control being included for use in emergency. A range of specially manufactured electric cables is available for road heating purposes, but because of their unique properties, the mineral-insulated types are preferred. Mineral-insulated road heating cables consist of a single-resistance alloy conductor, insulated by means of densely compacted, high-purity magnesium oxide, contained within a seamless copper sheath with an overall serving of PVC. The cable as a heating unit is terminated with a waterproof seal, fitted in the factory under ideal conditions. A variety of seals and terminations are available to suit all installation requirements. For the Blackfriars scheme, BICC mineral insulated road heating cables were specified, and these were supplied as factory-made units on drums, each drum containing some 12 individual 131 meters long units of 3 kilowatts loading per unit, complete with cold tails. Each unit length was designed not only to provide the required temperature to adequately heat the road surface, but also to ensure that when laid as mats, with cable runs at the appropriate spacing, the entire road area would be covered and uniformly heated in service. The cables were laid longitudinally, and the correct spacing of the cable runs was achieved by means of a temporary jig made up of 2 lengths of angle iron with spigots positioned at regular intervals along their length to act as formers. 2 lengths of timber constrained the angle irons in position to maintain the desired separation. Cable laying was preceded by the sweeping of the road surface to clear it of any debris. At the start of cable laying, the cold tail at the leading end was kept clear of the heating cable, being positioned just outside the jig, due regard having been paid to the exact positioning of the jig. The operation of cable laying is in itself very simple, consisting merely of drawing the cable off the drum and lacing it across the formers. The spigots on the angle irons give the correct spacing between cables, and the length of the timber restrainers is so calculated that when the mat is laid, the trailing cold tail will coincide with the leading cold tail, but on the opposite side of the mat. Altogether, heating mats were laid along the whole of the elevated roadway at Blackfriars, a distance of 152 meters, and later they were laid over the 244 meters long underpass, and also for a distance of 61 meters on the Bridgehead flyover, giving a total loading for the system of nearly 700 kilowatts.